everyone, I'm Meghamala, working as Assistant Professor in Electronics and Communication Department from IARE. Okay, today I'm here to talk about behavioral modeling, which is the third model from our subject, Digital Design through Verilog. So coming to this topic, behavioral modeling, let's have a recapitulation for the previous session. In the previous two modules, we have discussed about how Verilog acts as an HDL, and different constraints and all. And also we have discussed about three types of modeling. In order to design a circuit, particular digital circuit, in order to design and develop, the circuit has to go through three levels. Okay, so from the three levels, any one level it can be chosen by the designer. So the three levels would be circuit level or switch level, behavioral level, and gate level. Okay, so the designer has to it's all depends on the designer whether he wants to choose a particular module to be developed in terms of switch level, or else in terms of behavioral level, or else in terms of circuit level, and as well as in the gate level. Okay, so and already we had discussed what is the gate level modeling. In the gate level modeling, we had discussed about the designing or the development of a particular digital circuit will be made with the help of the gates. Okay, all the primitive gates. All the gates are well predefined already in the Verilog library. And also, in order to write the syntax for each and every module that a designer is going to design, he has to write this particular syntax. He has to he has to write a particular syntax, and in order to write the syntax, he has to go through some use some terminologies. Okay, so in order to write this syntax, he has to use some terminologies, and those terminologies are based upon the lexical tokens. Already we had discussed this in the previous class. So different lexical tokens have been used. They are by the usage of this lexical tokens, the designer has to draw the code. Designer has to write the code. Okay, a particular syntax has to be written by the designer by using the several lexical tokens. So coming under the lexical tokens, we had discussed about the primitives, we had discussed about the keywords, and we had discussed about the operators, different types of operators. And also we had discussed about and question mark. Okay, so these are the things which we had discussed in the lexical token category. And also we had discussed about the statements, continuous statement, assignment, continuous statement. All these we have discussed in the gate level modeling. Okay, continuous assignment statements, and also discontinuous assignment statement, net declaration statements, and so on. Okay, so all these different kinds of statements, whatever we had discussed in the previous session, each and every statement, or else each and every module, it represents something else. Okay, some specification has been considered for each and everything. When it comes to the continuous assignment statements, a word keyword code assign or begin, and also when it comes to the net declaration statement. Okay, in order to declare a particular net, the syntax has to follow the net. Under the net, wire is a keyword which we had used. Wire is nothing but it is a thing where the output of one particular gate has been connected to the, in order to connect the input of in order to connect the two gates. That means what? First, suppose output of this gate has to be connected to the input of this gate, right? So this is how the connection takes place using the wire. Okay, so this wire is a keyword where we use this keyword wire in the net assignment declaration statement. Okay, so and also we have discussed about the different examples coming under the combinational circuits or also sequential circuits. The different examples are like multiplexers, the basic examples, basic combinational circuits or the sequential circuits. We had discussed about the flip-flops, latches, and we had discussed about the multiplexers, demultiplexers, encoders, decoders, priority encoders. okay, and also magnitude comparator. All these different examples we have discussed in order to perform the gate level simulation, or else in the behavioral level simulation. Okay, and also we have discussed about the register transfer language. So how does the data transfer from one register to the another register? Okay, using programmable interface, logic interface, PLI. Using programmable logic interface, how the data has been transmitted between the registers. Okay, all these things we have discussed in the earlier sections. And now in this particular class, we are going to discuss about what is a behavioral modeling. Okay, it is one of the prominent modeling. It's a high level of abstraction. The highest level of abstraction can be made using this behavioral modeling. Okay, so this is the highest level of abstractions in the Verilog hardware descriptional language, and the abstraction in this modeling is simply as writing in the logic in C language. So when you compare the Verilog HTL and as well as the C language, we see there is some similarities. But though we have the little similarities between the C language and as well as the HTL language, but the thing we have to remember is Verilog HTL, it is a case sensitive language. Okay, it is a case sensitive language, but you will see some similarities between the C level language and as well as the Verilog HTL language. And also all that a designer need is the algorithms of the design, in which is the basic information for any design. So any designer, if he wants to design something, some module, he has to design that module with respect to the algorithm. So he need the algorithms in order to design some particular module. Okay, some particular combinational circuits or whatever the circuit, digital circuit. If he wants to design something, he has to. The designer must need the algorithms to perform it. And also, most of the behavioral modeling are done using two important constructs. So under this behavioral modeling, two important constructs has been considered. One is the initial and the second one is the always. Okay, basically in the previous sessions we have discussed when it comes to the syntax, depends upon the behavioral modeling, or it's a gate level modeling, switch level modeling, whatever it is. We had written the syntax with the help of these constructs, initial and as well as the always. Okay, so in the behavioral modeling, most of the behavioral modeling done using two important constructs. The important point, that is, first one is the initial and the second one is the always. And coming to the last point, all the other behavioral statements appear only inside of these two constructed procedure constructs. So all the statements, whatever the statements, usually in the syntax, we will start up with the initialization of the ports, input and output ports, and the declaration of the ports, and come to the statements, and we will end up the statements, and finally we will end module the whole thing, right? So we will see this initial and always only in between inside the statements. Okay, the behavioral statements appear only inside of these two constructs. Okay, it's not beyond these two constructs, but only inside. Whether it is always or else it is initial, only inside the construct we will see all the statements. Okay, and how it is we will see in the coming slides. And coming to the point, behavioral modeling in the Verilog, it contains a procedural statements. Okay, so why this procedural statement it contains means in order to control the simulation and also in order to manipulate the data, manipulate the variables of the data type. So here in the behavioral modeling, we can manipulate the data, manipulate the variables, and also in order to control the simulation, this behavioral modeling, it contains some procedural statements. Okay, and also each of this procedure has an activity for flows associated with it. So here we see in this behavioral modeling, there is no break in between the one procedure model to the other procedure model. You will see a continuous flow. A continuous flow has been seen in this behavioral modeling. There is no cut shorts. Okay, so the procedure has an activity flow associated with it. And also during simulation of the behavioral model, all the flow defined by the always and the initial statements, it starts together at the simulation of 0. So here in this particular statement is talking about the flow will contains all the flow it defines with respect to the always and the initial statement, and it starts with the simulation, the simulation parts will start with the 0. That means what? Input and as well as output, it starts with the same time constraint. Okay. And also the initial statements are executed once, whereas the always statements are executed repeatedly. Okay. So when you compare these two constructs, these two primitive constructs, important thing to be remembered is the initial statements are, they can execute it once. Okay, the initial statements are executed once, whereas the always statements, they can execute, or else they execute repeatedly. Okay, this is one of the important points. And coming to the procedural constructs. So this procedural construct topic is one of the main topic in this behavioral modeling. So what are this procedural construct? We will see in detail. We know that procedural constructs are nothing but the initial and always. Okay, so initial and always. So we will see how, where and what are these. So behavioral modeling is a predominant descriptive style used by industry, enabling the design of massive chips. So in order to design big chips, or else in order to design in order to construct complicated chips, most of the designers, they choose this behavioral modeling. Okay, so why? Because it has a predominantly descriptive style used by the industry in order to modify, or else in order to construct, or else develop the complicated chips. And also behavioral modeling, it describes what? The functionality of a design by specifying the design circuit will do, and not how to build it in the hardware. It just specify what the design circuit will do, what the circuit, whatever the designer is designing some module, what it will do. It will be discussed much, but it will not discuss how it will do. I mean to say, we just ponder on what it will do, what the circuit, whatever the designer has been designed some module, we just only consider, or else we just only concentrate on what the designer circuit will do, but we will not consider, or else it will not be taken into consideration that how it has built. Okay, this is a difference that you have to remember, that we will ponder on what, but not how. Okay, in the behavioral modeling. And also it specifies the input output model of logic circuits and suppressed details about physical gate level implementation. So it only concentrate on the output model of logic circuits. It only concentrate on the structure of the logical circuit, structure of the particular module, or a structure of the particular combination of the digital, whatever the digital circuits that you are considering. It is just mainly concentrate on the structural component, but it will not but it just suppress, or that means what? It will not consider about the details about the physical gate level implementation. Physically, we will not be concentrating much on the physical constraint, but only the structural part, that is how about the, it specifies the input output model of the logic circuit. Okay, and also it encourages the designers to, here we have 3 points. This behavioral modeling, it just encourages the designers. What it will encourage? It encourages the designers to rapidly create a behavioral prototype of a design, okay, without binding it to a hardware details. So this behavioral modeling, it just helps out the designer just to concentrate on a creative of a behavioral prototype. Okay, a behavioral some rules. In order to create some massive chips, the designer has to concentrate only on the creator, how to create, what sort of a circuit he has to create. He has to ponder on it, but not on the without considering the hardware details much. And also it encourages, this behavioral model, it encourages the designers to verify its functionality. Okay, first they will concentrate on the creativity. Rapidly they have to create the behavioral prototype in order to develop some circuit. And the second point is the functionality. Okay, they will verify the functionality, how it is implementing, how it is functioning, when you give the input, what sort of output is it getting, and all those functionality they will it will encourage. And also the designers, this modeling encourages the designers to use a synthesis tool to optimize and map the design into a selected physical technology. So what it does the synthesis. Okay, by using the synthesis tool in order to optimize and map the design to a selected physical technology, in order to map and also in order to design to a particular selective technology, they will use some synthesis tools. Okay, so these three steps, these 3 points, these behavioral modeling helps the designer to ponder on this and act accordingly. Okay, and also, okay, this behavioral modeling, it provides the freedom to explore alternatives to a design before committing it to production. So what does it mean? Behavioral modeling, it gives a chance, or else it gives a freedom in order to choose. It gives a freedom to choose whatever the construct, or else to choose and to explore the alternatives. They can go for the alternatives. If one way is blocked, they have the another way to choose. Okay, they have the freedom to choose the alternatives and to design before committing for the production. So before they commit in order to produce some in order to develop some circuit, they have a chance, or else they have a freedom to explore, okay, the alternative. They have a freedom to take the alternative decisions. Okay, and also behavioral modeling, it provides flexibility to a design project by allowing parts of the design to be modeled at different levels of abstraction. So this behavioral modeling, what it does is, it gives a flexibility, okay, at different levels. At level 1, for example, in order to develop a circuit, a complex circuit, that particular complex circuit, it has to go through 4 levels: level 1, level 2, level 3 and level 4. Okay, so if you consider me as a designer, now I have a chance, or else I have a flexibility that I can choose a easy way to design it. Okay, I have a freedom to take the alternatives. What is the best alternative in order to construct a particular model in a very short span? Okay, these are the advantages a designer can have if he wants to design a particular circuit in a behavioral modeling. Understand? So behavioral modeling, it provides a flexibility to design the project, allowing the parts to design to model at different levels of abstraction. So a designer, being a designer, he can have a freedom, or else he can have a chance in order to choose a level of abstraction. Okay, on which level he is comfortable in order to develop a particular circuit. Okay, so he has that freedom, he has that chance, he has that alternative to develop a particular complex or else a massive chip. Next, propagation delays are not included in the behavioral model of circuit. So this particular sentence is talking about the gate level modeling. So as we are discussing right now the behavioral level of modeling, as per these sentences, we have to remember the gate level modeling. In the gate level modeling, only the delays are observed. Already we have discussed different types of delays also as well. Okay, so in the behavioral modeling, there is no point of delaying. Okay, so propagation delays are not included in the behavioral model of the circuit. And also Verilog supports structural and behavioral modeling. As I said you, this behavioral modeling, it only talks about the structure of a particular structure of a particular complex circuit, structure of a particular module. Okay, so this Verilog, it supports a structure and as well as a functioning of the particular structure. Okay, it supports a structure and as well as a behavior of that particular circuit diagram, or it's a particular digital circuit. Okay, and the structural modeling connectivity, primitive gates and function, it uses units to create a specified functionality. For example, here the structural modeling, it connects the primitive gates. Yes, it's obvious. The sentences talks about very clearly regarding the structure. If for suppose I wanted to design some module. Okay, I want to design some computer. For example, if I want to design some computer, I have to design internally the big computer. It will have segregation has to be taken place, isn't it? Why? Because one part I have to make it for the storage purpose. Whatever the data I'm giving, it has to store. And the second one is for displaying purpose. And third one is for storing the video or else the audio purpose. Okay, so the complex module, it is comprised of all the small modules together forms a big module, isn't it? So here, this structural modeling, it's talking about the connects the primitive gates. So this particular module, internally it consists of so many gates. Okay, it is designed with so many gates. So in order to connect from one module to another module, the structural modeling connects the gates, primitive gates, for functional unit in order to create what? A specified functionality. For example, here he has taken adder. Okay, adder, what it does, it adds up. It adds the 2 bits and it gives the sum and the carry bit also as well. So using gate level modeling, AND gate, using AND gate and XOR gate, the adders have been the design, isn't it? Adders are designed using AND as well as the XOR gates. So that is a structure. Adder is having. We will design the hardware using some primitive gates and XOR gates. Finally, we will form into some structure, isn't it? So in order to create a specified functionality, just as spans are connected on a chips on a circuit board. So how it is, on a circuit boards, we will connect some pans, right? On a circuit board, we will connect some pans. Like, for example, if you consider a PCB, printed circuit board, if you see, many peripherals, many parts, many different tiny particles have been, tiny parts have been fixed on it, isn't it? So all the tiny particles fixed and it will forms into one structure. So here it states the same thing. Structural modeling, it contains the primitive gates and used to create a specified functionality just in order to connect on a chip on a circuit board. How the chip is connected on a circuit board, in the same fashion, we will be connecting all the different modules, all the peripheral modules in a big complex circuit board or a big complex chip. Next, behavioral modeling is a predominant descriptive style used by the industry, enabling the designers of massive chip. So especially in order to design complex chips, in order to design huge chips, basically designers will choose this behavioral modeling. Okay, behavioral modeling. Why? Because it is a predominant of the descriptive style. More than the structure, we will describe what sort of gates we have been used, or else in what way we are implementing. All the descriptive styles have been mentioned clearly in this behavioral modeling. And also behavioral modeling, it describes the functionality of a design. It describes the functionality of a design, that is, what is a design circuit will do and not how to build it in a hardware. So here, what does its sentence says, as we discussed in the previous slide, it's only concentrate on what is a designed circuit will do. What the designed circuit, whatever the circuit that you are designing, what it will do. But it will not concentrate on how to build it in a hardware. Okay, how to build in a hardware, we just don't bother. But only the thing we have to remember, or else we just keep on thinking that what the design circuit will do. Okay, the designers will always remember what the designer circuit will do finally. And behavioral modeling, it specifies the input-output mode. So this behavioral modeling, it specifies the input and as well as the output mode. So here is an example. In this particular example, we have the register variables A and B are initialized to binary 1 and 0 respectively at simulation time 0. So here we have A and also we have B. So at time t is equals to 0, the simulation time, both A and B, it starts propagating. Okay. So the register variables A and B are initialized to binary 1 and 0 with respect to a simulation at time 0, at t is equals to 0. Then the initial statement is completed. Now initializing has been completed and not executed again during the simulation run. When the simulation start, again we will not execute or else we will not execute it again. Why? Because in the initial statements, this initial procedural construct, once it started, it is fixed. There is no point of again executing again. Once it is started, it is fixed. Okay, once executed started, it is done. But when it comes to the always, it is repeated. Okay, so here the statement talks about the initial statement is completed, not executed again during the simulation. So during the simulation, it will not start again. Okay, it will not execute again and again. Next, this initial statement is containing begin end block of statements. So this initial state procedural consists of two types. One is the initial and one is the always, right? So this initial statement, it contains begin end block. So here begin, this is a module, add a port list, and here begin statements, and here and coming to end module. Okay, so here the initial statement is containing a begin and end. So this is nothing but the initial statement. So in the begin and end type block, A is initialized first followed by B. So when you are initializing the inputs, A should be initialized first. So int A, next int B. Okay, that's how we will initialize. First comes A and then comes B. So this is how the initialization of the initial construct, procedural construct takes place when you write the syntax. So this is the example. So if you look at this example here, you have module behave, register 1 0. That means what here? 2. Okay, 2 inputs, A and B. Register is a keyword. In the behavioral modeling, register is a keyword will be used in order to store the data. So here I am storing the 2 bits of data. Why? Because my inputs are A and B. Next, initial. I said you initial and begin. These are executed, not executed only once, but they are not repeated. Okay, initial. So here when it comes to the statements, initial, begin. A is nothing but bit 1 and B is second bit 0. So A is representing it with 1 and B is with the 0. And finally, we are ending up with the end. So this is what? Begin and end block. So initial statements containing a begin and end block of statements. So in this begin and end block type, A is initialized first followed by B, isn't it? So same here, A is initialized first and then followed by B. And finally, we are ending up with end. So here it is done with the initial. And next comes to the second procedural construct, that is always. Okay, so the second procedural always, again begin and end. So here in this particular 50, A is equals to not A. So this 50 is nothing but the delay. Okay, for example, 50 nanoseconds of delay. So I am representing it with 50A. That is where this is a particular and A. This is not of A. So here in this, both the input starts at 0 at time t is equals to 0. But when it comes to the when it comes to the what do we say? This A bar, we see my delay goes to 50 nanoseconds. That is what the representation. Okay, A complement is 50 nanoseconds of A. Then ending. Again, always we see. As I said you, this is executed only once. The initial will execute only once, whereas the always, it repeats. Repeatedly, we can execute always statement. Okay, always statement can be executed repeatedly, whereas initial statement, they can execute it only once. Okay, so here always begin at 50 nanoseconds. My A complement has been taking place, and then again it is, as I said you, always construct can be repeatedly executed, right? So again begin 100B, which is equal to minus B. So here my another B complement, my another input B complicate, it is rising up with 100 nanoseconds. Understand? So always it repeats, whereas initial it executes only once. And finally, I am ending up the sentence with end module. I have started with module behavior, and I'm ending up with the end module. Okay. Next. So, for example, here also the same thing. So module behave, register 1 is equals to 0. For example, in the register, if you want to store a data, you can also write register 5 is to 0 A comma B. What does it mean? I'm storing in the register 6 bits of data. Okay, so just to store the data, we are using a register. Register 5 is to 0 A and B. Now I'm initializing. Initial, it executes only once. Okay, it executes only once. And now I'm beginning. A is equals to B, A is equals to 1, B is equals to 0. And I'm ending up with this. And now initial is done. Initial is done. Now I have to go with the always. Always. And now in the always, I'm just representing the delays. Okay, with how much of delay both the inputs are taking place. So first initializing, previous it was 50, right? Now I want to take 20. Okay, 20 nanoseconds of delay. A bar. And again, as I said you, always are, they can execute it repeatedly. So, and here I'm going with the delay with 200 nanoseconds. So, one input, one complement of A is with 20 nanoseconds and complement of B is 200 nanoseconds. But both starts with the time 0. But the difference is always procedural constructs can be repeated, whereas the initial procedural constructs cannot be repeated, only they can executed once. So this is about the procedural constructs. We have two types of constructs, initial and as well as the always. Those two constructs can be written in the syntax in order to write any kind of syntax with respect to the different combinational circuits or logical circuits. Different digital circuits. If you want to write a syntax, we have to follow. This is a procedure to be followed. Initial is to be executed once. Always they can be executed once, twice, thrice, more than once. Okay, repeatedly we can execute the statement. So this is about the combinational behavioral modeling. In which we have discussed about the procedural constructs, and also we have discussed about the different types of what is a behavioral modeling in general, and what sort of the designers has to do. Okay, in order to encourage the designers, how this behavioral modeling is helping them. Okay, in order to construct, or else in order to build a massive chip, how this behavioral modeling is helping them to come out of with different difficulties that they are facing. Okay, and in fact to say compared to all the levels, different levels, behavioral, circuit, gate level, and as well as the switch level, I can say that behavioral modeling is the best way to choose in order to develop a particular module within a short span. And also here in this behavioral modeling, we just only concentrate only on the functionality of the particular circuit, functionality of a particular combination of whatever the digital circuits that you are considering. We just ponder only on the functionality of the particular circuit, but not on the physical structure of the circuits. The physical structure of this circuit will be constructed or else maintained by the gate level modeling. In the gate level modeling, we will be designing the circuit with the help of the primitive gates, which are already present in the Verilog library. Okay, so this is all about the behavioral modeling. And always remember that initial statements are executed once, whereas the always statements are executed repeatedly. In the example we have discussed, right? Initial statements, they execute only once, whereas repeatedly we can execute the as many as always statements. And also this is a very good model in order to develop a particular circuit which controls the simulation, and also for the manipulate the variables. We can manipulate the variables. And also here one more advantage of considering this behavioral modeling here is the designers, they have the freedom to choose the alternatives. Okay, the designers, they have the freedom to choose the other alternatives. They can choose the best option in order to develop, or else in order to develop or construct a particular massive chip, or else a complex chip. Okay, this is about the behavioral modeling. I hope you all understand, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.